All right, so this is the advanced stoichiometry problem. So firstly, when we're looking at these type of problems, what we want to do is we want to, obviously, as with every problem, look at the given and look at the want. Also, precursors to all of that, for this whole problem, I kind of wrote out everything that's needed for this type of problem, that some key checkpoints you want to hit as you go through it. So for this, we're gonna look at the balanced equation. Then we're gonna find moles. Obviously, always find moles. It's very important. Then we're gonna answer the first problem after this. And this is a little midway point, the limiting reactant. So from that, we're gonna go to the participant formed. And then we're gonna go to the ions, the second part of that question afterwards. All right. So, firstly, the balanced equation, and then setting up our given and our wants. So what we know is that we have K2SO4 plus CaNO32, and those go at those. So we don't know this. This I wrote this out already, but you should know this. Okay, it's the double double. It's like this goes here, this goes there. Easy. Y'all got that. Okay. Anyways, so we have this, and now we want the grams. We want the grams of what's formed. Okay, how are we gonna do that? Well, firstly, we're gonna find moles. Well, how are we gonna find moles? Well, obviously, we're gonna use the given, what's already known. So we're gonna start with K2SO4. We're gonna say, and we're gonna do liters, by the way, not milliliters. Tricking you with that. So we're gonna say 0.0100 liters times 0.100 molarity. That is equal to how many moles? Quick calculator check. That's gonna be 0.01. I'm not stupid, I swear. I just wanted to be sure. All right, now we're gonna do that for the second one, which is gonna be 0.100 liters, and then let's multiply times. That's gonna be equal to this. All right. I kind of forgot to do it just now, but it's very important that you label them. So this is going to be K2S. It's gonna be moles. The answer is gonna be moles. So M over L. Duh. M times L. So moles of K2SO4. This is gonna be moles of CaNO3. 2. All right, so now that we got our moles, we need to answer a question. That question is, which one of these guys is the limiting reactant? Well, for this problem, since it's a little easier, we could just compare these two straight up since there's no coefficients. But if there was a coefficient, what would you do? I'm gonna work it out anyways, okay? For y'all's benefit. Well, you'd say you'd go from the moles of this to the moles of whatever else, and you'd put the molar ratio in front of it. So you'd be like 0.01 moles of K2SO4, and that's equal to whatever the ratios were. Let's say there was like a 2 over here, or whatever. You'd put the numbers here. But for these, we just have ones. So 1 mole of K2SO4, and we're trying to find out the participant formed. And so we're gonna do 1 mole of CaSO4, and then this is so we have our limiting reagent. We already know it's gonna be this guy, and so what we could do is we could just find out how many grams for each, and we can just see which one's smaller, and then we can just keep the number. I wrote this down on the side for y'all. You just have to calculate it yourselves. We know how to do that. You've lasted this long. I believe in y'all. So you want to cancel out moles of CaSO4. So 1 mole CaSO4, and that's equal to 136.1 G over mole. And this number is going to be equal to 136.1. This is going to be equal to 1.361 grams. Same thing can be done with CaNO32. What you do is you just replace this here. And since the ratios are the same, it would just be 0.02 times that. But y'all don't need to see that since there's no molar ratio difference. The number would just be twice as big. But we're finding the limiting reagent. We want the smallest amount that is produced by one of these guys. And that's going to be this guy, since this is the smallest number. So we use our molar ratio. So we have our answer right here. 1.361 grams of CaSO4. Okay, that's review. Let's be honest here. We knew this. Here's where it gets a little more new, a little more familiar. We're going to be looking at the ion concentrations. As you can see, the concentration of the remaining ions. And so I wrote out a little map that I found useful, that I just committed to memory, that I think would be helpful for y'all. So there's gonna be three categorizations. You're gonna have spectators. You're gonna have spectators. You're also gonna have a zero, and you're gonna have because these fully consumed. We'll get there. And then you're gonna have the last one, which is gonna involve the limiting reagent, and you're gonna see how much is left of it. So let's go through all these and classify them, and I'll walk you through how to do that. Okay, so we have K plus. So how do we know? So this guy's a spectator ion. That's because he's not involved in the participant. So he's kind of just gone. Same thing with the NO3. So yes, the question, spectator. Yes. So if it's a yes, like these two guys, because they're not part of this that we are looking for, you just do a simple calculation of the moles of that substance divided by the total volume. Total volume. That's going to be 0.01 liters. 0.1 liter plus 0.1 liter. And that's going to be over the moles. And then you're not done there. Do not make the same mistake as I. You want to multiply that times 2 moles over 1 mole, because that's the molar ratio, the coefficient, because there's 2 of these for every one of these. And so that molarity is going to kick out, well, let's just do that real quick. All right, sorry for the delay. That's gonna be equal to 0.1. Duh. Stupid Jake. He's not good at using calculators. And then same thing for this. You should do the same type of calculation. So NO3, how many moles of that were formed in the end? 0.02, right here. Divided by the total volume. And then you're going to multiply that times the molar ratio. 0.2. See, this goes a little bigger. We knew this already. And so we got the S's down. So now there's 2 other categorizations, right? There's we have spectators, yes, and there's the fully consumed, and there's the one by the limiting reaction. So how do we know which one's fully consumed? Well, we go to our equation as always, and we look at this. Okay, so there's two parts of this. We have the Ca and the SO4. And then we look back at our limiting reagent, which we knew is the K2SO4, and we see if there's any of these guys inside of this. And if there is, that guy's gonna be fully used up, right? Just by simple logic, we know this already. That guy's gonna be fully used up. So, therefore, it's gonna be 0 moles, 0 molarity. That's pretty much just logic. That's you logicking the 0 out. And so, here comes the hard part a little bit. This is the limiting reagent. We know this because it's affected by the limiting reagent. It's Ca right here. So how do we calculate that? That's the question of the day. It's just as always back in the olden days. It's just total minus used divided by the total volume is going to give us our molarity. So our total, if we go up to the Ca, is 0.02. Let me use a different color here just to color code it for y'all's eyes. So our total is going to be minus how much is used. That's the question of the day, isn't it? That's why we use our limiting reagent. We go up here where the LR was. How much was used? How many moles? Right here, 101. And that's going to be divided by the total volume. Well, the total volume, remember that from over here, it's you add them together. So it's going to be 0.2 liters. And these are moles. Moles over liters equals molarity. Punch this into our handy dandy calculator. 0.05 m. And there you go. That's the that's for the Ca of Ca2 plus. And so now we have all of our all of these ions just kind of scattered about the place because I'm organized. Right here, right here, and then over here, and over here. And that should give you full credit for the test.